lies at the heart of everything we're trying to do in computational chemistry. So we're going to spend the next couple of weeks trying to understand some of the basic concepts and be able to look at how we apply molecular orbital theory in doing computational chemistry. So let's go ahead and get started. Some of the key concepts in quantum mechanics that you need to have in your head a little bit, and some of these may be familiar, some of these may be new to you, are things like the Heisenberg uncertainty principle, which says it's really pretty hard to define where the electron is in an atom or where the electrons are in a molecule. So we're pretty uncertain about where things are, and as a result of that, in computational chemistry and in quantum chemistry, we're really dealing a lot with probabilities. The good news is the computer is really good at being able to calculate these probabilities for us and do a lot of the mathematical heavy lifting for us. But Heisenberg basically said that we really don't know where the electrons are, but we can make some intelligent statements about where they might be and how that affects the behavior of the molecule. You also need to understand the concept of an atomic orbital. And what that means is electrons live somewhere near the nucleus. So the electrons will live in some volume or in some space somewhere around the nucleus. And that space is what's known as the atomic orbital. Okay? And when we're talking about computational chemistry and quantum chemistry, really what we're trying to do is calculate the probability of where an electron might be in any given atomic orbital. And you had a chance to do that a little bit with the spreadsheet lab several weeks ago, where you were calculating the curves and looking at with the hydrogenic orbitals and looking at where it's most likely that we might find an electron given its distance from the nucleus. And you also need to know that electrons have what we call spin. So you can, in any one orbital, in any one atomic orbital, we can only have 2 electrons. And we say that those spins have, or those electrons have spin. We say they have spin up or spin down. The mathematicians aren't really happy with the choice of the language up and down, so they say an electron that has a spin up has a value of 1/2, and an electron that has a spin down has a value of -1/2. And basically, fundamentally, they're opposite. You know, we could have said boy and girl, up and down, left and right, yes and no. And again, for most of the time, we're going to say up and down. Again, the mathematicians like to say +1/2 and -1/2. Okay? So you need to understand that electrons do have spin, and that's an important characteristic of electrons and how they behave. Okay, the main thing that you have to understand at the beginning levels of molecular orbital theory is this idea of an atomic orbital. And there are different types of atomic orbitals. Every atomic orbital can hold 2 electrons. So we start out with what's known as the s orbital, and the s actually doesn't stand for spherical shape. S stands for there's a German term that was used to define these orbitals many years ago, but it's convenient that the s is an easy mnemonic to help you remember that the s orbital has a spherical shape. And basically the electrons can be located anywhere within that sphere centered at the atom's nucleus. So somewhere in that red ball there, and you see the dark nucleus in the middle, anywhere inside that red sphere, inside that red ball, there will be the probability of finding 1 or 2 electrons. Can't be any more than 2, because that's all we can put in a particular orbital. The next type of orbitals are known as p orbitals, and there are 3 types of p orbitals, and we call them p sub x, p sub y, and p sub z, reflecting, of course, the 3-dimensional coordinate system. And what you might notice about these orbitals is they have a figure of 8 shape. They have lobes to them. And if you notice that there's a blue lobe and a red lobe, and those correspond to sort of the state of the wave function. If you read in the chapter on molecular orbital theory, you should have read that wave functions have an up part and they have a down part. And we use a color coding that blue means that the wave function is in its up condition, and red we use to mean down or in its negative position. And just like before, the positive and negative really don't mean charge. We're not talking about negative charge or positive charge. Basically, we're just using red and blue to say we're in the up part of the phase, and red to be we're in the down part of the phase. So you'll have to learn how to interpret these orbital pictures, and you'll see lots in red and blues in the lab you're being asked to do this week. So again, and each of these p orbitals can hold 2 electrons. So the total number of electrons that a p level can hold is 6. So 2 in the px, 2 in py, and 2 in pz. When you get into the transition metals, those are the elements in the middle of the periodic table, the zincs, the irons, the golds, the silvers, the coppers, the cobalt. We will have electrons there on what are known as the d orbitals, and there are 5 types of d orbitals: d sub xy, d sub xz, dyz, dz squared, and dx squared y squared. And these are very complex looking orbitals. They're higher in energy than the s and p orbitals. In the lab you're being asked to do this week, we'll ask you to take a look at zinc, so you'll be able to look at some of these orbitals and see what they look like. But 90% of the work that we're going to do, or have been doing in computational chemistry so far, really is focusing on those elements and those atoms, those compounds that are only dealing with s orbitals and p orbitals. If you want to do some computational chemistry around metals, then you would have to pay attention to d orbitals, and that requires a little bit more work on your part. Okay, but you should know that they exist. Okay. Now, obviously you know that every element is different. Every element in the nucleus has some number of protons that determines the identity of the element. There's a number of electrons that determines the overall charge, and the number of neutrons determines which isotope of the element that happens to be. And I hope you've experienced that in a beginning chemistry course at some time in your career. As we've talked about with the Born-Oppenheimer approximation, we really don't pay much attention to the nuclei. We consider them to be big, heavy objects that don't move very fast as compared to the electrons. So really all chemistry is done at the electron level, or as we say, at the electronic level, and that's why knowing where the electrons are and what they're doing is really important. And an electron configuration is a way to describe where the electrons are in any given atom, okay? And this basically electron configuration talks about which atomic orbitals are the electrons in. And we can organize our atomic orbitals by energy level, by something called a subshell, orbital levels, spin levels, what they call the quantum numbers. Good news is we won't spend much time on quantum numbers in computational chemistry. We'll sort of take a swing around quantum numbers just because we don't see them used a lot. They're there, but we don't really have to deal with them in terms of computational chemistry. Okay, so let's take a look at this, and what I'm showing you here is both an electron configuration and an orbital diagram, or orbital filling diagram for lithium. Lithium has 3 electrons, so what we do is we start out by putting 2 electrons in what's called the 1 level. And in the 1 level, the only kind of orbital in a 1 level is an s orbital. So what you've seen there in the green box at the bottom labeled 1s is an arrow pointing up and an arrow pointing down. Those arrows are used to represent electrons, and notice I have the arrow pointing up and an arrow pointing down. That means I have spin up and spin down, and again, like the mathematicians like to say, plus 1/2 or minus 1/2. By the way, you can do the mathematics on that. Plus 1/2 minus 1/2 is 0. So there would be no charge. There would be no charge in that 1s orbital. Okay? And the way I would write that notation would be 1s2. You don't read that 1s squared because we're not squaring s. The 2 as a subscript there just tells you that there are 2 electrons in the 1s level. Okay, lithium, as you know, has 3 electrons, so where do I put the 3rd electron? That goes all by itself at a higher energy level in the 2s level. Okay, so in the 2s, we typically notate it as having a spin up. We could have just as easily put it as spin down, but convention says we usually put it as a spin up. So I can either draw this orbital diagram, or some people call it an orbital filling diagram, or I can simply write the notation 1s2, 2s1, and it's certainly a lot easier to write 1s2, 2s1 than to draw this picture every time. And again, any chemist worth his or her salt understands what you're talking about when you say 1s2 and 2s1, and you'll need to be able to do that as well. And the lab will help you do that. Okay, so here are some example electron configurations for the first 5 elements: hydrogen, helium, lithium, beryllium, and boron. Total number of electrons, 1, 2, 3, 4. And I've done sort of an abbreviated orbital filling diagram there. You should know in the orbital diagram, as I go from left to the right, the energies are getting higher. And you see my electron configuration notation, 1s2, 1s1, 1s2, going all the way up to 1s2, 2s2, 2p1. And we'll ask you to do this in the lab this week. Okay, we can write electron configurations in some sort of shorthand notation so that we don't get anything that's real long. As obviously, if we get to have 50 or 60 electrons, it gets pretty tedious to write that. And so the shorthand way is to write the electron configuration for our noble gas, and then and those are called the core electrons, and then simply write the valence electrons. So for sodium, we would write neon as the core. Neon there will be 8 electrons in there, 1s2, 2s2, 2p6, 10 electrons. And then sodium has 11 electrons, so the 11th electron goes in the 3s1 level. And we can do the same thing for lithium there, and you should play with that and make sure you understand that. And again, the electrons in the noble gas configuration are called the core electrons, and anything outside of that are called the valence electrons. Here's an orbital filling diagram that gives you an idea, and probably the most helpful thing is the thing at the bottom. So the 1s2, 2s2, 2p6, and it shows you how we fill these things. And again, you'll find these diagrams everywhere. This is called an off-bow AU-FBAU filling diagram, and these are pretty easy to find. They're in every chemistry textbook, and you can find a million of them on the web. So if you're not sure what order the electrons go, you would use this. And again, the good news for us is we're really going to be mostly paying attention to s and p orbitals. We're not going to be worrying too much about filling up d's or f's, so that should be good news for all of you. Okay, like I said before, valence electrons are the electrons on the outside, the outermost area of the atom, and the ones that are on the inside are called the core. Some of the older notation, by the way, we used to call these things K, L, and M. That's a little older notation, but core and valence are all you're going to need to know for this particular course and for most of chemistry. Okay, here's some other examples of electron configurations. We won't spend much time on this, but notice, by the way, that fluorine as an atom is a 1s2, 2s2, 2p5 with 9 electrons. And if I make it an ion, if I make it F negative, then we have to add an electron to the electron configuration. So now it's 1s2, 2s2, 2p6. And that's more of importance to those of you who might be taking AP chemistry than it really is in terms of computational chemistry. The good news is the CompChem server is pretty smart and it's going to figure out all of this stuff for you, but you need to be able to do this by hand, at least on a pretty basic level. Okay. All right, molecular orbital theory. The goal of MO theory is to describe molecules in a way similar to how we describe atoms. We want to talk about orbitals. We want to and orbital diagrams and electron configurations. Now, in molecular compounds, we don't have S's and P's. We only have those in atomic structures, elements. Okay, but we're going to have something very similar to that, and that's what we'll talk about next. Okay, you need to understand that molecules can form bonds by sharing electrons. Okay, so anytime, and 2 shared electrons form a single bond. So anytime you see 2 atoms connected together with a line or a stick, in your head you have to understand that that stick represents 2 electrons. So a single bond is going to have a pair of electrons, a double bond is going to have 2 pairs of electrons, a triple bond is going to have 3 pairs of electrons. Okay? And mostly what we're going to concern ourselves with in computational chemistry, at least in this course, are covalent bonds, where those electrons are being shared between 2 atoms. And we will maybe have a chance to talk about ionic bonds and metallic bonds, but for purposes of this conversation, we're really going to concentrate on covalent bonds. Okay, so what's really important is this concept of orbital mixing. If you have 2 atoms, and that's what you have here at the top of your picture there, you have 2 hydrogen atoms. You see the orange nucleus in the middle. You see the 2 blue dots there. Each of those represent an electron, and they're spinning around the nucleus. Okay, and those are both s orbitals, so that's a hydrogen 1s and a hydrogen 1s. And what happens if these things have similar energy levels, what they will do is they will overlap. So what you see here is I've taken two s orbitals and I have overlapped them, and because they overlap, they form what's called a bond. Okay. Now, it's not quite this simple, needless to say. If I show you this next diagram, okay, there are, what you're seeing here is sort of a complicated looking graph, but it's actually not too hard. If you look at the very top, if I have too much overlap, then everything's going to repel. The two nuclei are going to be too close to each other and they're going to repel, and that's going to be a high energy state, not going to be very stable, and they're not going to want to stay that way very long. If I have just the right distance between the two atoms, I get just the right amount of overlap between the orbitals. This is sort of a Goldilocks and Three Bears thing, not too hot, not too cold, just right. So if I have just the right amount of distance between the two atoms, then I get just the right amount of overlap, and that results in a really low and really stable energy level. And it turns out for hydrogen, that length, that distance between the nuclei is about 74 picometers, or about 0.74 angstroms. Okay? If I get too far away, if the atoms are too far away, I get some overlap and some attraction, but not enough to really make a stable bond. And obviously, if they're real far apart, they can't overlap at all. They can't touch each other. So there's no overlap, there's no attraction, there's no bond. Okay, so you should take a look at this picture here and really make sure you can make some sense of it and go from there. Okay, this is probably the best graphic in the entire presentation. So what I'm showing you here, starting at the top, if I take a hydrogen with its 1s orbital and another hydrogen with its 1s orbital, okay, and I put them at just the right distance, about 74 picometers, they're going to overlap in just the right way that they're going to create a hydrogen-hydrogen bond. And we call that bond a sigma bond. So we went from s orbitals to a sigma bond. So when we're talking about molecular orbitals, we don't talk about s's and p's, we talk about sigmas, okay? And we'll also eventually talk about pi in a minute. Okay, and going down to the next graphic, if I take a hydrogen with its 1s orbital and the fluorine with its 2p, and I let those two bump up against each other, I will get an overlap there. And notice the shape of the sigma bond in the hydrogen fluoride. Notice you can see a little bit of the what used to be the P shape, and I tack on a little round spherical thing, so it puts a little bubble on the end of the P there. You should also notice, by the way, that the P orbital there has sort of a light blue and a dark blue sides to it. Notice that when I'm bonding or mixing or overlapping with the hydrogen, I have the dark blue overlapping with the dark blue. Okay, the colors always need to match. When we do this on the server, you're going to have red and blue p orbitals. Reds always overlap with red. Blues always overlap with blue. Reds never overlap with blue, and blues never overlap with red. So you notice there I got the two dark blues that are overlapping, and that forms the HF sigma bond. Okay, the last example, and we'll do this one in the video conference on Thursday night. I have a 2p orbital of fluorine. I have a 2p orbital of another fluorine. I align them so I have the light blue facing the light blue. The light blues will overlap. They'll form, again, a sigma bond, and I get that funky looking shape there. It looks like a donut in the middle of two pi lobes there. So, and we'll let you take a look at that tomorrow night on the server. And again, that's called a sigma bond. So the important thing in molecular orbital theory is going to be knowing what the lobes are, okay, what color they are they red or blue, and then we can talk about whether or not they'll overlap and make a bond. Okay, so we have other ways of being able to communicate what these things look like, and these are called molecular orbital diagrams. And they get very complicated very quickly. We'll practice with some simple ones. What you should know getting into them is each line in the diagram represents an orbital, and that the volume of the molecular orbital encompasses the whole molecule, so you'll have lots of lines, and the molecule volume is from top to bottom. Okay, the electrons will fill in the molecular orbitals, as you'll see in a minute, and just like the electrons fill atomic orbitals in atoms. So again, if I look at just atoms, Okay, electrons go in the lowest energy level, so if I have 2 electrons, they're going to go in the 1s orbital. The next 2 are going to go in the 2s. The next one's going to go in one of the p orbitals. The next one's going to go in one of the p orbitals. If I had one more electron, it would go in the 3rd p orbital. And again, you should know by now the maximum number of electrons is 2. That's called the Pauli exclusion principle. Okay, one electron goes up, one goes down. They pair up. That's Hund's rule. And electrons can change their spin. If you have 2 up electrons and you put them together, one of them will switch sides and go and be a down electron. So they can switch their spins. Okay, so here's a molecular orbital diagram for hydrogen. Okay, it looks pretty complicated. If you start over on the left-hand side, what I'm showing you with that line there labeled 1s, that's the 1s orbital of a single hydrogen atom. Okay, and it has 1 electron in it, and by convention we put it as spin up. If you look on the right-hand side, you see the other hydrogen atom, and it too is a 1s orbital with an electron, 1 electron in it, and I have it spin up. And if I put these two things together, the 2s orbitals will overlap, and again, it's 74 picometers. And when they overlap, it turns out that they become more stable. In other words, the energy goes down, and that's what you see there in the middle where it says molecular orbital. So notice that the line there in the middle labeled sigma, that's a sigma bond, is at a lower energy level. So what that's telling you is a hydrogen molecule, H2, is more stable, lower energy, than 2 hydrogen atoms by itself. Hydrogen really doesn't like to be by itself. It really wants to pair up with another hydrogen, and when it does so, the whole thing gets to be more stable and everybody is happy. So notice that there are 2 electrons at that low energy level called the sigma bond, or the sigma orbital. Okay? All right, so there's a picture of it again. Now, okay, what would happen if I had a 3rd electron? Suppose I had for somehow I got a 3rd electron in here. Where would that 3rd electron go? The only place that it can go is in the next orbital up, and that's labeled sigma star. And any orbital that has a star on it is called an anti-bonding orbital. Obviously, anything that doesn't have a star on it, like the sigma at the bottom, that's a bonding orbital. So in this case, what you're seeing is a bonding molecular orbital, that's the line on the bottom, and a anti-bonding molecular orbital, that's the one on top. Okay, wow, look at this, complicated. Here's the molecular orbital diagram for oxygen. If I start on my left-hand side, okay, I look at oxygen, I have 8 electrons, I have a 1s2, a 2s2, and then I have 3 p orbitals, 2px, 2py, and 2pz. And given that I have 8 electrons, I put 2 in the 1s, 2 in the 2s. 2 of them will go in the 2px, 1 will go in the 2py, and the 8th one will go in the 2pz. And I do the same thing on the other side for the other oxygen atom. And now when I do my filling, in the middle you're seeing the molecular orbitals. So what do I get? I get a bonding orbital, that's the sigma 1s. I get an anti-bonding orbital, that's the sigma star 1s. Okay, I'm moving up. Then I get a bonding orbital, sigma 2s. Then I get an anti-bonding orbital, a sigma star 2s. Okay, moving up, I get a bonding orbital, sigma 2 pi. And now I'm going to get what are known as pi orbitals. Okay, and those are the overlap of p orbitals. So I get a pi 2p, and notice that there are 2 of them, and each one of them contains 2 electrons. And then moving up to the next level, I get a pi star 2p. That pi star is a pi anti-bonding orbital. Okay, and we'll practice some of these by hand, and you'll get really good at drawing molecular orbital diagrams, and you'll enjoy it very much. Okay, here are some other ones that get a little bit more complicated. So here I'm showing hydrogen fluoride. I have my fluorine over on the left-hand side. I didn't draw all the electrons in. I've got my hydrogen over on the right-hand side. There's my 1s hydrogen. And I have a total of, looks like 8 electrons, 2, 4, 6, and 8. And you can see which orbitals they go into. They go into a 1 sigma, a 2 sigma, and into a pi. Okay. And so notice that the energy levels there are slightly not quite as even, and we'll talk about that. We'll actually do some of these experiments computationally where you can actually calculate these energy levels. Here's one for methane, CH4. You see the single carbon atom over on the left. You see the 4 hydrogens over on the right, and you can notice there how we're filling up the sigma and pi molecular orbitals there. And again, that's one we'll try to do on the server so you can actually see what these orbitals look like. Okay. Again, they get very complicated very quickly. Here's a molecular orbital diagram for oxygen. Oxygen's on the left, the 2 hydrogens are on the right. And again, these different levels. And again, what you will do in various labs is, again, try to use the server to calculate these energy levels and tell us why it's important. For example, if you notice in the molecular orbital there, the one at the very bottom there labeled 1A1, look how far away that orbital is from the, if you can see it there, the 2B2, the next one up, okay? There's a lot of energy difference between those two orbitals, but there's not as much energy difference between the second one, the third one, and the fourth one. And those energy differences make a whole lot of difference, and that's the thing that tells us whether or not this molecule will be reactive or not. And we'll spend a lot of time calculating those data points. Okay, some of the key concepts are bonding electrons are localized between atoms. What that means is if you have bonding electrons, you're going to find them right in the middle between 2 electrons, and that's called localized. Okay? You should understand that we can take atomic orbitals like an s orbital and an s orbital, and we can overlap them to form bonds. You need to understand that 2 electrons of opposite spin can occupy an overlapping orbital. You need to recall that these electrons can change spin. You need to understand that bonding increases the probability of finding electrons in between atoms. So bonding is a good thing. It makes the whole system more stable. And you should also understand that it's possible for atoms to form ionic and metallic bonds, and we'll spend some time talking about that later on in the course. If you have any questions, we'll see you online, and I hope this was an interesting conversation. See you online.